Welcome to Starsky Science. Before we begin unraveling one of the most fascinating mysteries of the cosmos, make sure to subscribe so you never miss our deep explorations into the universe's greatest secrets. Now, let me ask you something extraordinary. What if the universe itself could sing? Not in the way we hear with our ears, but in a deeper, cosmic rhythm ripples that stretch across space-time itself. These are gravity waves, and today, they're reshaping our understanding of reality. For centuries, humans stared into the night sky, wondering how the universe works. We could see the stars, map the planets, and measure the pull of gravity on Earth. But there was something hidden, something Einstein himself predicted more than 100 years ago: waves, rippling through the very fabric of space-time. Invisible, inescapable, almost impossible to detect. Gravity waves are not like light or sound. They don't bounce off walls or scatter in the air. Instead, they travel unhindered, carrying whispers of the most violent events in the cosmos: colliding black holes, exploding stars, neutron stars spiraling into each other. Each wave is a message, a coded note from the universe's most extreme phenomena. But why are they so elusive? Imagine trying to measure a shift in distance smaller than the width of a proton. That's the scale of precision required to detect a gravity wave. For decades, scientists dreamed of capturing these signals, but the technology simply wasn't there. And then came 2015. The world of physics held its breath as the Laser Interferometer Gravitational Wave Observatory LIGO made history. For the first time, humanity detected a ripple in space-time, caused by two black holes colliding more than 1 billion light-years away. It wasn't just a confirmation of Einstein's prediction, it was the birth of a new era of astronomy. Think about it. Before LIGO, we explored the cosmos with light. Telescopes showed us stars, galaxies, and quasars. But with gravitational waves, we opened a brand new sense, like suddenly gaining the ability to hear after living in silence. The universe had always been playing this symphony. We just finally built the instrument sensitive enough to listen. That first discovery in 2015 changed everything. The signal, lasting just a fraction of a second, told us about two massive black holes spiraling into each other, merging in a cataclysm that released more energy in an instant than all the stars in the observable universe combined. Let that sink in. More energy than billions of galaxies compressed into a single ripple across space-time. Since then, the discoveries have only grown richer. LIGO, along with its European partner Virgo, has detected dozens of gravitational wave events. Each one reveals secrets invisible to normal telescopes. We've seen neutron stars colliding, giving rise to heavy elements like gold and platinum, the very stuff that makes our jewelry and electronics possible. Yes, the gold on your finger may have once been forged in the cosmic fire of merging neutron stars, its story carried across the universe by gravitational waves. And the advancements don't stop there. Recently, scientists have gone beyond simply detecting waves. They are now uncovering patterns, background signals, and even hints of waves from the earliest moments after the Big Bang. Imagine tracing the faint echo of creation itself, hidden in the fabric of space-time. That's where new research is leading us. But what does this mean for us? Why should we care about something so abstract, so distant? Because gravitational waves give us a direct connection to the most extreme objects in the universe. They allow us to study black holes, not just as dark voids, but as dynamic entities we can listen to. They let us test Einstein's theories under conditions so extreme, they were once thought unreachable. And they may even hold clues to solving the greatest mysteries of all: the origin of the universe, the nature of dark matter, and the unification of physics itself. The more we listen, the more surprising the universe becomes, and the latest discoveries are unlike anything we expected. Scientists are now detecting signals that challenge our models of black holes, suggesting that they may be spinning or merging in ways we don't yet fully understand. Some signals are so strange that researchers wonder if we've stumbled upon entirely new types of objects, like primordial black holes from the dawn of time, or exotic stars made of matter we've never seen before. And this is just the beginning. The next generation of detectors, like LISA, the space-based Laser Interferometer Space Antenna, will open our ears to a new range of frequencies, allowing us to hear waves from supermassive black holes at the centers of galaxies, or even the faint whispers left over from the Big Bang itself. With each advancement, we're not just adding data, we're rewriting our understanding of reality. Here's the astonishing part. Every time we detect a gravitational wave, we're not just observing the event, we're traveling back in time. These waves have been traveling across the cosmos for millions, sometimes billions of years before reaching Earth. When LIGO detected that first signal in 2015, the black holes that caused it had collided long before Earth even existed as it does today. We are, quite literally, listening to history written in space-time. And yet, for all we've learned, so much remains unknown. What exactly happens at the heart of a black hole? Do gravitational waves carry information that could one day reveal the unseeable? Could they unlock a unified theory of physics, bridging Einstein's relativity and the mysteries of quantum mechanics? These are the questions driving scientists forward. So as we unravel these cosmic ripples, one truth becomes clear. The universe has been singing all along. We just needed the right instrument, the right patience, and the right curiosity to finally hear its song. And remember, this is only the beginning of our exploration. Subscribe to Starsky Science so you can stay with us as we dive deeper into the discoveries that are transforming our view of the cosmos. The universe is calling. Let's listen together. Gravity waves are not just an abstract prediction anymore. They are a frontier of experimental science. But here's the real question. How do we even detect something so impossibly small? After all, gravitational waves stretch and squeeze space-time itself by less than the width of a proton. Capturing them is like trying to measure a shadow moving across a ruler 1,000 times smaller than an atom. The answer lies in one of the most remarkable scientific instruments ever built, the Laser Interferometer Gravitational Wave Observatory, better known as LIGO. Picture two massive tunnels, each 4 kilometers long, set at right angles to each other, like an enormous L shape carved into the Earth. Inside these vacuum-sealed tubes, lasers are fired and bounced between mirrors suspended with almost supernatural precision. When a gravitational wave passes through, it stretches one arm while compressing the other by a distance smaller than anything humans have ever attempted to measure. The lasers interfere with each other, producing a pattern that reveals the tiny distortions in space-time. This is interferometry, a technique so sensitive it can detect changes in distance smaller than 1/10,000th the diameter of a proton. But the story of LIGO isn't just about engineering brilliance, it's about perseverance against decades of doubt. Back in the 1960s and 70s, scientists dreamed of detecting gravitational waves, but the technology was crude, and the signals were buried in noise. Many physicists argued it was impossible that Einstein's prediction would remain untestable forever. Yet, a small group of visionaries believed it could be done. Among them was Rainer Weiss, whose early designs laid the foundation for LIGO. His idea: suspend mirrors in vacuum chambers and measure the stretching of space-time with lasers. At the time, it sounded crazy. Today, it has earned him a Nobel Prize. But even with Weiss's vision, LIGO faced endless obstacles. Seismic noise, tiny vibrations from earthquakes, ocean waves, even trucks passing miles away could drown out the signal. Thermal noise from atoms jiggling in the mirrors could mimic gravitational waves. Cosmic rays, electronics, and random glitches, all of these had to be accounted for. To succeed, LIGO needed innovations at every level: advanced laser stabilization, seismic isolation platforms, and mirror coatings polished to near perfection. By the 1990s, construction began, fueled by collaboration between Caltech, MIT, and the U.S. National Science Foundation. For years, LIGO ran quietly, picking up nothing but noise. Critics grew louder. Was this an expensive failure? Then came a breakthrough. The observatory underwent a massive upgrade, advanced LIGO. The mirrors became larger, the lasers more powerful, and the sensitivity vastly improved. And then, on September 14, 2015, history was made. Two black holes, 1.3 billion light-years away, collided, and Earth trembled ever so slightly. The lasers picked it up, and humanity had its first direct evidence of gravitational waves. What's fascinating is how clear the signal was. The waveform matched exactly what Einstein's equations predicted for merging black holes. For a fraction of a second, space-time itself rang like a bell, and we caught it. But LIGO didn't work alone for long. Soon after, the Virgo Observatory in Italy joined the hunt, and together they triangulated sources more precisely, narrowing down the regions of the sky where signals originated. Japan's Kagra, built deep underground in the mountains, became another crucial partner. And in the coming decade, the European Space Agency will launch LISA, a space-based detector with arms millions of kilometers long, orbiting the Sun to capture the lowest frequency gravitational waves. Think about this. Humanity is building a new sense, an entirely new way to observe the universe. Before telescopes, we only had our eyes. With telescopes, we saw light across the spectrum: radio, infrared, X-rays, gamma rays. Now, with gravitational waves, we can feel the universe. It's as if we were deaf, and suddenly, after millennia, we've begun to hear the cosmic symphony. But here's a hidden challenge. Gravitational waves are rare and fleeting. The detectors are so sensitive that a falling tree miles away or a truck driving near the observatory can mask or distort the signal. Scientists spend months analyzing each detection, separating genuine cosmic events from background noise. The process is rigorous. Every signal must appear in multiple detectors, must match theoretical models, and must survive countless tests against false positives. Only then can it be declared a true gravitational wave event. What does this mean for astrophysics? Quite simply, it's revolutionary. For the first time, we can study black holes directly. Before 2015, black holes were invisible except for the light from matter falling into them. Now, we can measure their masses, spins, and orbits by listening to their mergers. We can map populations of black holes across the universe. Already, gravitational wave detections have revealed black holes larger than astronomers expected, challenging old theories of stellar evolution. And then there are neutron stars. In 2017, LIGO and Virgo detected the collision of two neutron stars, dense stellar remnants just a few kilometers wide but heavier than our Sun. This wasn't just a gravitational wave detection. It was a cosmic fireworks display. For the first time, telescopes across the world captured light, gamma rays, X-rays, and radio signals from the same event. Astronomers called it a multi-messenger discovery, a turning point in science. And it proved something extraordinary. The collisions of neutron stars forge heavy elements like gold, platinum, and uranium. The jewelry we wear, the coins in our pockets, all of it may have been created in such violent cosmic mergers billions of years ago. Gravitational wave science doesn't just tell us about cosmic collisions, it's starting to hint at deeper mysteries. Could we detect waves from the earliest moments after the Big Bang, when the universe itself was stretching faster than light? Could we find signals from exotic objects like quark stars or even theoretical cosmic strings? These are no longer just dreams, they are serious scientific goals. Every detection, every signal, brings us closer to understanding the laws of physics under extreme conditions. General relativity has passed every test so far, but gravitational waves may eventually expose its limits. Perhaps they'll reveal cracks in Einstein's great theory, pointing the way toward a unified theory of quantum gravity. Imagine detecting a ripple in spacetime that defies our equations. That would mean a revolution in physics as profound as Einstein himself. And what about the future? With planned upgrades, LIGO will become even more sensitive. LISA, launching in the 2030s, will capture signals from supermassive black holes millions of times the mass of our Sun. Pulsar timing arrays using millisecond pulsars as cosmic clocks are already hinting at a background hum of gravitational waves across the universe. Each method, each new discovery, expands our awareness of the cosmos in ways we never thought possible. We are not just observing the universe, we are listening to it breathe, stretch, and evolve. When Albert Einstein published his general theory of relativity in 1915, he didn't just rewrite physics, he reshaped reality itself. The theory replaced Newton's concept of gravity as a simple force with something far more profound. Space-time itself could curve and bend under the influence of mass and energy. According to Einstein, planets orbit the sun not because of an invisible pull, but because the sun's immense mass warps the geometry of space-time, guiding the planets along curved paths. But hidden in Einstein's equations was an even stranger implication. If massive objects moved suddenly, like stars colliding or black holes spiraling inward, they could send ripples across space-time itself. These ripples, traveling at the speed of light, were what we now call gravitational waves. Yet even Einstein wasn't sure. At first, he predicted them. Then he doubted them. In fact, in 1936, Einstein himself, along with his collaborator Nathan Rosen, submitted a paper claiming gravitational waves might not exist at all. The paper was even rejected by a leading physics journal, sparking one of the most famous back-and-forth debates in science. Eventually, after revising his calculations, Einstein reaffirmed their existence. But this confusion left physicists uncertain for decades. The real problem was detectability. Even if gravitational waves were real, they were absurdly small. Imagine two neutron stars colliding billions of light years away. The waves reaching Earth would distort space-time by less than 1 part in 10 quadratsoon. To put that in perspective, that's like changing the distance from Earth to the nearest star by less than the width of a human hair. How could anyone possibly measure that? Enter Joseph Weber. In the 1960s, this physicist built the first experimental devices designed to detect gravitational waves, known as Weber bars. These were massive aluminum cylinders, designed to vibrate ever so slightly when a gravitational wave passed through. Weber claimed to have detected signals multiple times, sending shockwaves through the physics community. Headlines proclaimed a new era of gravitational astronomy had begun. But soon, doubts crept in. Other scientists built similar detectors but found nothing. For years, Weber defended his work, but eventually, his claims were discredited. No one could replicate his results. Still, his efforts weren't wasted. They inspired a new generation of physicists who believed detection was possible even if Weber's bars weren't the answer. This pursuit pushed technology forward. Laser interferometry, once just a laboratory curiosity, began to emerge as the true solution. Decades of refinement eventually led to the construction of LIGO. And when that first detection finally came in 2015, it wasn't just a triumph of technology. It was a vindication of a century of doubt, debate, and determination. The lesson here is powerful. Even Einstein, even the greatest scientific minds, can question their own predictions. Science isn't about certainty. It's about testing, failing, correcting, and pushing forward until the truth reveals itself. And in the case of gravitational waves, the truth was worth waiting for. But perhaps what makes this story even more extraordinary is what it reveals about human persistence. Think about it. Generations of physicists spent their lives chasing something invisible, something that might not have even existed. Some lost credibility. Others were mocked. But they continued, not for fame, not for money, but because curiosity demanded it. And in the end, they opened a new window on the universe. Now that gravitational waves are no longer just theory, their impact is spreading across the entire landscape of science. They are no longer just a niche branch of physics. They are becoming a bridge between fields once thought separate. Cosmologists are using gravitational waves to probe the very expansion of the universe. By analyzing the signals from neutron star mergers, scientists can measure distances across space without relying solely on light. This creates a new kind of cosmic ruler, helping us refine the value of the Hubble constant, the rate at which the universe is expanding. Interestingly, this may help resolve one of the biggest mysteries in modern science. Why do different methods of measuring cosmic expansion give slightly different answers? Could gravitational waves settle the debate, or will they deepen the mystery? Particle physicists, too, are intrigued. If exotic objects exist like hypothetical boson stars, cosmic strings, or dark matter clumps, gravitational waves might reveal them. Unlike light, which can be blocked or scattered, gravitational waves pass straight through matter. They could expose hidden structures in the universe that no telescope can see. And then there is the connection to quantum physics. At the tiniest scales, gravity refuses to play by the same rules as other forces. By listening to gravitational waves, especially from extreme objects like black holes, scientists may one day uncover hints of quantum gravity, the long-sought unification of Einstein's relativity and quantum mechanics. This could be the breakthrough that defines physics in the 21st century. But beyond the equations and data, gravitational waves touch something deeper. For the first time, humanity can not only see the cosmos, we can hear it. Every detection is a note in a universal symphony, played out over billions of years and billions of light years. It is a reminder that we are not separate from the universe, we are participants in it. And perhaps this is the most profound revelation of all. These waves don't just tell us about distant stars, they tell us about ourselves. The gold in our jewelry, the elements in our bodies, the very matter that makes Earth all of it, was forged in cosmic events that sent gravitational waves echoing through the universe. When we detect them, we are, in a sense, listening to our own origins. So as the science expands, so does our imagination. What else is hidden in space-time's ripples? What messages from the past are still traveling toward us? And what new secrets will we uncover as detectors grow more sensitive? The truth is, we are only at the dawn of this field. The discoveries of today are just the first chords of a much larger symphony still waiting to be heard. And at Starsky Science, we'll continue listening together. If you haven't subscribed yet, now is the time. Join us as we explore the waves, the forces, and the mysteries that will define the future of astrophysics. One of the most astonishing things about gravitational waves is that we can actually listen to them. Of course, space itself is silent in the traditional sense. There's no air to carry sound. But when gravitational waves pass through detectors like LIGO, the tiny distortions they create can be converted into audio signals. And when scientists did this for the very first time in 2015, what they heard was nothing short of breathtaking. It wasn't a roar, or a thunderclap, or some endless cosmic hum. It was a chirp, a rising note, lasting just a fraction of a second. Two black holes, each many times the mass of our sun, had been locked in an orbital death spiral for millions of years. As they drew closer, they moved faster, circling hundreds of times per second. And when they finally merged, they released more energy than all the stars in the visible universe combined. On Earth, billions of light years away, that entire event was translated into a sound, a faint, quick chirp. That chirp carried within it an incredible amount of information. From the shape of the waveform, scientists could deduce the mass of each black hole, the speed of their merger, even the way they were spinning. A sound lasting less than a second revealed details of an event that occurred more than 1 billion years ago. Since then, dozens of other chirps have been recorded. Each one is different. Some rise quickly, like a bird call. Others drag slightly longer, as neutron stars lighter than black holes spiral together. When two neutron stars collided in 2017, the chirp lasted over a minute, a long dance that ended in a kilonova explosion. And unlike black holes, neutron stars can produce light, which astronomers observed across the entire electromagnetic spectrum. But why does listening matter? Because the human ear is uniquely good at detecting patterns. When converted into sound, even subtle differences in gravitational waves become easier to analyze. Scientists can identify variations that hint at unusual physics, black holes spinning at unexpected angles, stars with uneven masses, or objects that may not even fit our current categories. And sometimes, the signals surprise us. Some detections show black holes heavier than we thought possible, suggesting that stellar collapse can produce giants far beyond old theoretical limits. Others raise questions about whether some of these objects could be primordial black holes, formed in the earliest moments of the universe. Think about that. Every chirp we hear might not just be an echo of a cosmic collision, it could be a clue pointing to the dawn of time. Listening to space-time has also become a powerful teaching tool. When people hear the actual sound of merging black holes, it bridges the gap between the abstract and the real. Suddenly, gravity isn't just a theory or a distant phenomenon, it becomes audible, almost personal. it becomes something we can experience directly. And perhaps that's why gravitational waves have captured the public imagination in a way few scientific discoveries have. For the first time, we are not only seeing the universe, we are hearing its music. But gravitational waves are more than sounds, they are cosmic messengers. Each wave is like a postcard sent across billions of light years, carrying news of the most violent events in the cosmos. By decoding these signals, scientists are uncovering secrets that light alone could never reveal. Take neutron star collisions. When LIGO and Virgo detected gravitational waves from the G170,817 event in 2017, telescopes across the globe turned their gaze toward the source. What they saw was extraordinary, a kilonova, a brilliant explosion that forged heavy elements. For centuries, we wondered where gold and platinum came from. Stars like our sun can forge lighter elements, carbon, oxygen, iron, but not gold. The answer was hidden in these cataclysmic collisions. Every piece of gold on Earth, every bit of platinum in our technology, every atom of uranium that powers reactors, all of it was born in neutron star mergers. Without them, Earth would be a very different place. This discovery was only possible because of multi-messenger astronomy, the combination of gravitational wave detection, with traditional observations of light, neutrinos, and other signals. For the first time in history, humanity watched a single cosmic event through multiple senses. It was as if the universe had been speaking in whispers all along. And suddenly, we learned to listen with both ears and eyes. The potential here is enormous. Imagine detecting a gravitational wave from a supernova in our galaxy and simultaneously watching it unfold in light and particles. We could map the physics of stellar death in unprecedented detail. Or imagine tracing waves from merging supermassive black holes at the centers of galaxies, learning how galaxies grow and evolve. And then there are the philosophical implications. Gravitational waves remind us that the universe is not static, it is alive, dynamic, constantly reshaping itself. They connect us to events unimaginably distant, both in space and in time. When we detect a wave today, we are receiving a message from an event that may have occurred billions of years ago, before Earth even formed. To listen to gravitational waves is to listen to history itself. And this is only the beginning. The next generation of detectors will hear farther, deeper, and clearer. They will reveal events we cannot yet imagine. Some may even capture the faint hum of the Big Bang itself, a background of primordial waves that would take us back to the universe's very first heartbeat. Imagine standing at the edge of existence itself, listening not with your ears, but with instruments capable of sensing vibrations in the very fabric of space-time. These vibrations, these ripples we call gravity waves, are not random whispers in the dark. They are messages from the universe's most violent, powerful, and mysterious events. And in the last few years, the clarity of these messages has grown sharper than ever before. Now, let's turn our attention to one of the most profound questions. What do gravity waves reveal about black holes and neutron stars? And how are these discoveries rewriting the story of our cosmos? When Albert Einstein first proposed gravitational waves in his theory of general relativity in 1916, he hinted at the possibility that massive bodies in motion could ripple space-time like stones tossed into a pond. But he himself doubted they could ever be measured, let alone traced back to their source. Over a century later, those ripples have become our most powerful tool for peering into phenomena that no telescope can ever show us directly. Black holes are at the heart of this. They are, after all, the ultimate distorters of space-time. With gravitational fields so strong that not even light can escape, black holes are silent in terms of traditional astronomy. No visible light, no X-ray spectrum, nothing that allows us to see beyond the event horizon. And yet, when two black holes spiral toward each other and collide, they unleash a torrent of gravitational energy. The waves that emerge from these cosmic dances are astonishing. In the split second of collision, they can release more energy than all the stars in the observable universe combined. For decades, this was only theory. Then came September 14, 2015, when LIGO detected gravitational waves from the merger of two black holes over 1 billion light-years away. That moment confirmed Einstein's vision and gave humanity its first direct evidence of black hole mergers. But that was just the beginning. Since then, detections have poured in. Each event carries its own unique gravitational fingerprint, revealing the masses, spins, and distances of the black holes involved. Some were small, about 20 times the mass of our Sun. Others have been enormous black holes so massive that their existence challenged previous theories of stellar evolution. And the discoveries have raised fascinating new questions. For example, we've seen black holes merging at masses that shouldn't even exist according to earlier models of how stars live and die. How do these massive black holes form? Are they the remnants of stars, unlike any we know today? Or are they born from earlier black hole mergers in a cosmic chain reaction? Gravity waves are giving us clues. Each ripple tells a part of the story, and when scientists map these waves, they can reconstruct the final moments before a black hole collision with stunning precision. But the story doesn't end with black holes. Some of the most groundbreaking gravitational wave detections have come from neutron stars, the ultra-dense remnants of massive stars that exploded in supernovae. Imagine a mass greater than the Sun compressed into a sphere only 20 kilometers across. A teaspoon of neutron star matter would weigh billions of tons. When two neutron stars spiral toward each other, the result is both violent and illuminating. Unlike black holes, neutron stars still contain matter, exotic, compressed matter that we cannot reproduce on Earth. When they collide, not only do they generate gravitational waves, but they also unleash electromagnetic radiation across the spectrum: gamma rays, X-rays, visible light, and radio waves. This was witnessed spectacularly in August 2017, when LIGO and Virgo detected gravitational waves from a neutron star merger. Just seconds later, telescopes around the world captured the event as a burst of gamma rays, followed by a fading glow across multiple wavelengths. For the first time in history, we observed both gravitational and electromagnetic signals from the same cosmic event. The significance of this cannot be overstated. It proved that neutron star collisions are the factories of heavy elements like gold, platinum, and uranium. In fact, much of the gold in your jewelry and the uranium that powers reactors on Earth likely originated in the violent death dance of two neutron stars billions of years ago. Through gravitational waves, we are literally listening to the cosmic forges that created the material foundations of our world. The science doesn't stop at detecting collisions. Each neutron star merger offers insights into the physics of matter at extreme densities conditions that cannot be reproduced even in the most advanced particle accelerators. As these stars tear each other apart, gravitational waves encode information about the stiffness of neutron star matter, about whether their cores hide exotic states of matter like hyperons or even quark-gluon plasma. In other words, by analyzing these waves, scientists are probing the behavior of matter at the frontier between nuclear physics and astrophysics. This is where discoveries become not only mind-blowing, but paradigm-shifting. Neutron stars, once thought of as cosmic curiosities, have become laboratories for fundamental physics, accessible not through sight, but through the vibrations they imprint upon space-time. And then there are the hybrid events, black hole neutron star mergers. These are rarer, but just as intriguing. In these cosmic encounters, a black hole consumes a neutron star, sometimes shredding it before swallowing it whole. The resulting gravitational wave signals are unlike any other part black hole merger, part neutron star destruction. What's remarkable is that these events may help solve one of the great cosmic mysteries: the origin of short gamma-ray bursts. For decades, astronomers have observed bursts of high-energy radiation lasting just seconds, but the source remained uncertain. Now, with gravitational wave detections, we know many of these bursts come from neutron stars colliding or being devoured by black holes. Through these cosmic ripples, we are not just observing violent events, we are connecting decades of astronomical puzzles, weaving together threads of theory, observation, and experiment into a coherent tapestry of understanding. The field of gravitational wave astronomy is growing at a staggering pace. With upgrades to LIGO, Virgo, and Kagra, the sensitivity of these observatories is improving, allowing us to detect fainter and more distant signals. In the coming years, detectors like LISA, the Laser Interferometer Space Antenna, a space-based gravitational wave observatory, will open entirely new windows into the universe. LISA will be capable of detecting gravitational waves from supermassive black holes, millions of times more massive than our Sun merging at the centers of galaxies. These are events so powerful that the ripples could be felt across the universe. Imagine the scale, the merging of black holes, each tens of millions of solar masses, sending out space-time tremors that travel billions of light years, only to be captured by a precise array of satellites orbiting the Sun. With LISA, we will be able to listen to these low-frequency cosmic symphonies, complementing the high-frequency detections of LIGO and Virgo. And this expansion of capability isn't just about scale, it's about diversity. Different observatories will pick up different classes of events, together building a full-spectrum understanding of gravitational phenomena. Now, one might ask, why does this matter to us here on Earth? The answer lies in the perspective it offers. For centuries, humans have sought to understand their place in the cosmos. Gravitational waves are not just another data point, they are a revolution in how we perceive the universe. They connect us to events unimaginably distant in time and space, reminding us that the elements we carry in our bodies and the very ground we stand upon are forged in these cataclysmic processes. And as we refine our ability to detect and interpret these waves, we edge closer to answering some of the most profound questions. How do black holes grow and shape galaxies? What is the nature of matter at the highest densities? Could gravitational waves even reveal hints of new physics beyond Einstein's relativity? These are not abstract questions. They are central to our quest to understand existence itself. So as we continue this exploration, stay with Starsky Science, because the ripples we are detecting today may soon transform into the keys that unlock the universe's most enduring secrets. And if you haven't already, don't forget to subscribe. This is just the beginning of discoveries that will shape science for generations to come. When we speak of cosmic events of unimaginable scale, we often think of stars colliding, galaxies merging, or black holes swallowing entire solar systems. Yet, within those events lies a faint whisper: gravity waves. These ripples in space-time, first predicted by Albert Einstein in 1916, have become the very fingerprints of the universe's most violent dramas. And in this era, with sensitive instruments like LIGO and Virgo, scientists are not just listening, they are beginning to decode this whisper into stories that redefine cosmic history. But what truly makes these waves revolutionary is not just their existence, but what they carry within them. They don't simply tell us that two black holes collided. They tell us how massive those black holes were, how fast they spiraled, how far they were from us, and sometimes even hints of the environment in which they merged. Every wave is like a telegram from deep space, a coded letter that physicists must translate to unlock truths about the cosmos. Consider for a moment the distances involved. Many of the waves we've detected so far come from black hole mergers billions of light years away. That means these ripples in space-time have been traveling for longer than life itself has existed on Earth. They've crossed vast, empty stretches of the universe, untouched, until finally, after eons, they made the mirrors of LIGO tremble ever so slightly. That in itself is awe-inspiring, that we, as a young civilization, are capable of detecting the faint heartbeat of an event that predates our very species. Now, one of the most fascinating aspects of recent discoveries is that these waves don't just confirm Einstein's theory of relativity, they test it. For over a century, Einstein's equations have stood as the bedrock of modern physics. But scientists have always wondered, are they complete? Could there be cracks in the theory? Cracks that only appear under the most extreme conditions in the universe. With each detection, researchers scrutinize the signals, comparing them to the predictions of relativity. So far, Einstein seems undefeated, but even the slightest anomaly, a fraction of a second where the wave doesn't behave as expected, could open the door to new physics, perhaps even a quantum theory of gravity. Imagine, after decades of searching, finding the first hint of a new law of nature hidden inside the faint tremor of a black hole collision. And this is where the story takes an even more extraordinary turn. Gravity waves don't just come from black holes. They can also be generated by neutron stars, incredibly dense remnants of supernova explosions. In 2017, scientists observed an event where two neutron stars collided, producing not only gravity waves, but also a spectacular burst of light across the electromagnetic spectrum. For the first time, humanity observed an event through both gravitational sound and electromagnetic sight. This was a revolution called multi-messenger astronomy. Why does that matter? Because it allowed scientists to study the same event from two completely different angles. Gravity waves revealed the motion and mass of the stars, while telescopes revealed the fireworks of the collision, including the creation of heavy elements like gold and platinum. Yes, the very gold in your jewelry, the platinum in electronics. Much of it was forged in cosmic collisions like these, moments when neutron stars smashed together and scattered their elemental treasures into the universe. So when you think of gravity waves, don't just think of them as abstract science. They are, in a very real sense, part of our personal story. They are connected to the atoms in our bodies, the metals we value, and even the life that has blossomed on Earth. And yet, these discoveries also raise questions. If gravity waves can show us the creation of elements, can they also show us something even deeper? The birth of black holes themselves, or the first stars in the early universe? Scientists believe that with more advanced detectors in the coming decades, we may even be able to listen to the very first moments after the Big Bang, a time when the universe was nothing but an ocean of energy and particles. Imagine actually being able to hear the sound of creation itself, encoded in space-time ripples billions of years old. But here lies the challenge. The universe is noisy. Not in the way our world is noisy, but in the sense that billions of cosmic events overlap, creating a background of gravitational hum. Detecting faint signals from this sea of noise is like trying to pick out a single voice in a crowded stadium. Yet, scientists are building techniques to separate these overlapping waves, hoping to uncover individual stories hidden in the background. One of the most ambitious efforts to achieve this involves the concept of space-based detectors. The LISA mission, Laser Interferometer Space Antenna, scheduled for launch in the 2030s, will place 3 spacecraft in a triangular formation millions of kilometers apart, orbiting the Sun. By measuring tiny changes in their distances, LISA will be able to detect gravity waves that Earth-based observatories can't. These include waves from supermassive black holes, giants, millions of times the mass of our Sun, colliding in distant galaxies. Think of what this means. Not only will we detect collisions of stellar black holes, but we'll also detect the titanic dances of galactic monsters. Every wave recorded will be a cosmic drumbeat, telling us how galaxies formed, evolved, and merged over billions of years. We'll finally have a tool to map the hidden skeleton of the universe itself. And speaking of mapping, recent research has suggested that gravity waves might even help us measure the expansion of the universe. Traditionally, astronomers have used light from distant galaxies to measure how fast space itself is stretching. But gravity waves could serve as what scientists call standard sirens, cosmic markers that tell us distance with remarkable accuracy. If successful, this method could solve one of the biggest puzzles in modern cosmology: the tension between different measurements of the universe's expansion rate. Just imagine, a century ago, we didn't even know the universe was expanding. Today, we're debating how fast it's expanding, and gravity waves may provide the final answer. That is the power of this new science. And while all of this sounds almost like science fiction, it is happening now. In laboratories, control rooms, and observatories around the world, researchers are tuning their instruments, analyzing terabytes of data, and waiting for the next cosmic ripple to arrive. Every detection is another step into the unknown, another whisper from the universe. At this moment, humanity has only begun to scratch the surface of what gravity waves can reveal. With more advanced detectors, international collaborations, and the creative insights of scientists across the globe, the next few decades may bring discoveries that completely transform our understanding of the cosmos. We've seen how gravitational waves revealed the hidden dances of black holes and neutron stars, but that is only the beginning. Now, let's look at how these ripples in space-time are beginning to illuminate the most extreme, bizarre, and exotic environments in the cosmos realms, where our existing physics begins to bend, and sometimes even break. For centuries, astronomers have observed supernovae, the brilliant explosions that mark the death of massive stars. These blasts can outshine entire galaxies for a brief time, but their inner workings have always been shrouded in mystery. Why? Because the very core of a supernova collapse happens in total darkness, hidden inside a star's dense layers. Photons, the messengers of light, cannot escape that turbulent chaos. But gravitational waves don't care about barriers. They ripple straight through matter, carrying pristine information from the star's collapsing heart. Imagine being able to listen directly to the core of a star as it implodes, instead of just watching the fireworks from the outside. That's exactly what gravitational waves promise us. Recent theoretical models suggest that the chaotic convulsions inside a dying star create a unique gravitational wave fingerprint, a pattern of ripples that could tell us whether the collapse formed a black hole, or perhaps a neutron star, or even stranger, an exotic quark star. We've already learned that neutron stars are incredibly dense, packing more mass than our sun into a sphere the size of a city. But physicists wonder, is that the ultimate limit of matter, or could there be something beyond? Here's where gravitational waves get exciting. When neutron stars collide, they squish each other in unimaginable ways before merging. That violent process imprints specific details into the gravitational wave signal, clues about what matter is doing at densities far beyond anything achievable on Earth. Some scientists speculate that the cores of these stars might briefly form quark matter, a soup of fundamental particles stripped of their normal bonds. If true, gravitational wave signals could reveal it, like a hidden fingerprint of exotic physics that no other method could uncover. And then, there are even stranger possibilities. The early universe might have produced vast, thread-like objects known as cosmic strings, defects in space-time itself, stretched across the cosmos like cracks in ice. For decades, they were purely theoretical, but gravitational waves offer a way to detect them. If two cosmic strings snap or collide, they could unleash bursts of gravitational waves unlike anything else. Detecting such a signal would be nothing less than discovering relics from the earliest moments after the Big Bang. But the mysteries don't stop there. Let's talk about one of the greatest puzzles in science: dark matter. We know it's out there. Its gravity shapes galaxies, bends light, and sculpts the large-scale structure of the universe. But we don't know what it is. Could gravitational waves help? Some theories predict that dark matter might clump or interact in ways that produce detectable ripples in space-time. For instance, ultralight dark matter particles could subtly alter the orbits of black holes or the dynamics of neutron star mergers, leaving subtle imprints in the waveforms. If future detectors achieve the sensitivity required, we might finally peer into the invisible side of the cosmos. And then, the even bigger mystery: dark energy, the force driving the accelerated expansion of the universe. Gravitational waves, traveling across billions of light years, might hold clues here too. Unlike light, which can be absorbed or scattered, gravitational waves carry a clean record of cosmic expansion. By comparing gravitational wave measurements with traditional observations, scientists hope to test whether dark energy truly behaves like Einstein's cosmological constant, or if it evolves with time. At the deepest level, gravitational waves may also give us hints about the unification of physics itself. General relativity describes gravity on the large scale, while quantum mechanics rules the small. The two theories don't yet fit together, but maybe, just maybe, gravitational waves can help bridge the gap. Some speculative ideas suggest that at extremely high energies, gravitational waves might carry imprints of quantum effects, like tiny echoes or distortions. Detecting these would open a door into the long-sought theory of quantum gravity. NASA scientists, along with international teams, emphasize that we're only scratching the surface. Every new detection provides a dataset unlike any before, and each ripple is a potential clue to unseen physics. European projects like LISA, the Laser Interferometer Space Antenna, planned for the 2030s, aim to detect low-frequency waves that ground-based observatories like LIGO cannot. With such missions, we may soon listen to mergers of supermassive black holes, primordial waves from the birth of the universe, and possibly exotic sources we can't even imagine yet. And here's where the excitement truly lies. Every unexpected detection has the potential to rewrite physics. Remember how the first discovery in 2015 was more than just a scientific win? It confirmed that black holes existed in binary systems and that they merge in dramatic ways. Nobody had ever observed that directly before. Similarly, the next breakthroughs in supernova detection, cosmic string evidence, or dark matter signatures could redefine our place in the universe once again. So, as you listen to this unfolding story of gravitational waves, remember, these aren't just abstract ripples. They are the universe speaking to us in a new language. A language that reveals hidden chapters of cosmic history, that challenges our understanding of matter and energy, and that brings us closer to answering the deepest question of all. Why does the universe exist the way it does? And if you're enjoying this cosmic exploration with Starsky Science, don't forget to hit that subscribe button. More incredible discoveries are waiting, and you won't want to miss them. The deeper we push into the mystery of gravity waves, the more we realize that these ripples are not just cosmic echoes of cataclysmic events. They are the universe's private storytellers. They whisper to us tales of phenomena that would otherwise remain hidden behind curtains of darkness, unreachable by even the sharpest telescopes. And in recent years, scientists have begun to uncover something remarkable. Gravity waves are not limited to just collisions of massive objects, but may also emerge from processes we had long overlooked. When we think of gravity waves, the first mental image is often of two black holes colliding in a grand cosmic dance. And yes, those collisions produce the strongest and most easily detectable signals. But what about the smaller, subtler events? What about the whispers rather than the shouts? This is where things get fascinating. Researchers at NASA, the European Space Agency, and other institutions are now developing techniques to listen to faint gravity waves that may come from neutron star quakes, supernova explosions, or even the vibrations deep inside massive stars long before they collapse. These are events that traditional astronomy often misses. Telescopes may catch a flash of light, but light alone tells only part of the story. With gravitational waves, we can now hear the vibrations of space-time itself, granting us a new sense, almost like an entirely different way of perceiving reality. Imagine being able to hear the heartbeat of a dying star, or sense the distortion of space-time as matter collapses into a singularity. That is precisely where we are headed. One of the most compelling areas of research is the study of continuous gravitational waves. Unlike the short, violent bursts caused by black hole mergers, continuous waves are steady, rhythmic signals that might come from rapidly spinning neutron stars. These stars, only about 20 kilometers across yet more massive than our Sun, are so dense and extreme that their slightest imperfections, tiny mountains, no bigger than a grain of sand, can send out a constant gravitational hum across the cosmos. Detecting this hum is like listening for a single faint violin string vibrating in the middle of a thunderstorm. Yet, if we manage it, the scientific rewards could be immense. Think about it. Continuous gravitational waves could allow us to map the interior of neutron stars in ways that no telescope ever could. These are objects so dense that a teaspoon of their material would weigh billions of tons on Earth. Their matter is compressed into exotic states, creating particles and forces that defy our current physics. Understanding them could push us closer to unlocking the long-sought theory of quantum gravity, a framework that unites general relativity and quantum mechanics, the two great pillars of modern science that currently don't agree on the universe's deepest scales. But here's where the plot thickens. Many researchers believe that gravitational waves could even hold clues about the Big Bang itself. Unlike light, which was scattered and absorbed in the hot plasma of the early universe, gravitational waves would have traveled through unimpeded, carrying a pristine record of the first fraction of a second after the cosmos was born. If detected, these so-called primordial gravitational waves would be like an ancient fossil of creation itself, written not in stone but in space-time. This is why observatories such as the Cosmic Explorer in the United States and the Einstein telescope in Europe are being designed with unprecedented sensitivity. Their goal is not only to detect more black hole collisions, but to reach further back into epochs of the universe we've never been able to probe before. With each new advancement, we're not just adding data, we're rewriting the very timeline of the cosmos. And then there is the mystery of dark energy and dark matter, two invisible components that dominate our universe. Together, they make up about 95% of the cosmos, yet we know shockingly little about them. Could gravitational waves help us peer into this shadowy domain? Some scientists believe so. For example, collisions of black holes at different distances could act like cosmic markers, helping us measure how fast the universe is expanding. By comparing these measurements with what we know from light-based observations, we might finally uncover hints about the nature of dark energy. Even more provocative is the suggestion that exotic forms of matter, like hypothetical cosmic strings, remnants from the early universe, might emit unique gravitational wave signatures. If we were to detect such signals, it would be like stumbling across an ancient artifact from a time when the laws of physics themselves were being forged. Now, let's pause for a moment and reflect on just how radical this is. For centuries, humans relied only on light to understand the universe. We built bigger and sharper telescopes, from Galileo's simple lens to Hubble, and now the James Webb Space Telescope. Each leap opened breathtaking new views. But gravitational waves are something entirely different. They are not light at all. They don't bounce off surfaces. They don't scatter through dust clouds. And they don't fade with brightness. Instead, they carry raw information about motion, mass, and energy itself, delivered directly across the fabric of space-time. In a way, it's like discovering that the universe has always been playing music, and only now are we building the instruments sensitive enough to hear it. But here's where things get even more exciting. Some astrophysicists believe that in the coming decades, we may not only detect gravitational waves from stars and black holes, but also from entirely new, unexpected phenomena. What if the universe is brimming with exotic objects we've never imagined, like boson stars, hypothetical structures made entirely of fundamental particles? Or what if tiny distortions left over from the quantum fluctuations of the Big Bang ripple through the cosmos even today? These are not just wild theories. They are testable, and gravitational waves could be the very key to proving them. One of the most ambitious projects on the horizon is the Laser Interferometer Space Antenna, or LISA. Unlike ground-based detectors, which are limited by Earth's vibrations, LISA will orbit in space, forming a triangle of satellites millions of kilometers apart. By measuring changes in the distance between these satellites with mind-boggling precision, LISA will be able to detect gravitational waves from sources far too subtle for Earth-based instruments. Think supermassive black holes merging at the hearts of galaxies, billions of light years away, or even the delicate tremors of exotic cosmic phenomena. The possibilities are staggering. LISA might reveal how galaxies evolve, how massive black holes grow, and perhaps even whether space-time itself has hidden layers beyond Einstein's equations. It's not just about observing, it's about challenging our most fundamental assumptions about the universe. And this brings us to one of the most profound questions of all. Are we on the verge of a new era of physics? Every time humanity has developed a new tool to sense the cosmos, we've uncovered realities we never dreamed of. Galileo discovered moons orbiting Jupiter. Hubble revealed the expansion of the universe. Could gravitational wave astronomy be the doorway to the next great paradigm shift, one that finally unites the vast cosmos with the smallest quantum realms? Have you ever wondered what the universe sounds like when it's screaming in its most violent moments? Not with light, not with color, but with ripples in the very fabric of space-time itself. And friends, before we go further, let me quickly remind you, if you're fascinated by these discoveries, make sure to subscribe to Starsky Science right now. We're only just scratching the surface, and trust me, the next revelations about our universe will leave you questioning everything you thought you knew. Now, back to the science. In earlier discussions, we explored the nature of gravitational waves, their detection, and their role in unlocking hidden cosmic structures. Now, let's turn our attention to something even more astonishing: how these waves are letting us witness the universe's most catastrophic and extreme events. the kinds of events that were once invisible, hidden behind shrouds of gas, dust, and darkness. When we think of the universe, we often imagine distant galaxies, stars gently glowing, or planets orbiting in quiet harmony. But beneath this serene picture lies chaos, colossal explosions, stars collapsing, and black holes colliding with unimaginable force. For centuries, astronomers could only watch these events through light, visible light, radio waves, X-rays, and gamma rays. But gravitational waves opened an entirely new sense, almost like giving humanity ears for the first time. Instead of just seeing the universe, we could now hear its most violent heartbeat. Take, for instance, the collision of two black holes. When this happens, vast amounts of energy, more than all the stars in the visible universe combined, are released in just fractions of a second. But almost none of that energy escapes in light. Instead, it escapes as gravitational waves, rippling outward across space-time at the speed of light. Until LIGO first detected such an event in 2015, this was purely theoretical. Now, it has become reality. Each new detection is like listening to the universe's ultimate symphony, a track recorded not in light, but in space-time itself. Another cosmic event that gravitational waves are beginning to illuminate is the supernova, the spectacular death of a massive star. When a star many times larger than our Sun exhausts its nuclear fuel, it can no longer support its own weight. Its core collapses in on itself, creating a dense remnant, either a neutron star or a black hole. The outer layers, meanwhile, blast outward in a titanic explosion, briefly outshining entire galaxies. We've long studied supernovae with light, but the most crucial moments, the collapse of the core, the exact mechanism that triggers the explosion, are hidden deep within the star, invisible to telescopes. This is where gravitational waves shine. If detectors capture the gravitational waves from a supernova, they could finally reveal the inner workings of this process. Scientists believe the chaotic motion of matter, neutrinos, and magnetic fields inside the collapsing star creates a distinct gravitational wave signature. By analyzing this signal, astrophysicists can uncover the step-by-step story of a star's final breath, something humanity has never directly witnessed before. Imagine being able to pinpoint exactly how a star dies, not just by the fireworks we see in space, but by the actual pulse of space-time it creates. That's the power gravitational waves bring to the study of supernovae. One of the most mind-blowing discoveries in recent years came in 2017, when detectors captured gravitational waves from a collision of two neutron stars. These are stars so dense that a teaspoon of their material would weigh as much as a mountain on Earth. When two neutron stars spiral together and merge, they create a burst of gravitational waves unlike anything else. But here's the part that truly reshaped science. The aftermath of such collisions forges heavy elements like gold, platinum, and uranium. Yes, the gold in your ring or necklace was not formed inside an ordinary star. It was forged in the fires of colliding neutron stars billions of years ago and scattered across galaxies by cosmic explosions. This single discovery tied together gravitational wave astronomy, astrophysics, and even the story of Earth's elements. For the first time, we weren't just guessing, we had direct evidence of how the universe manufactures the raw ingredients of planets, minerals, and life itself. Every time we detect a new gravitational wave event, it acts like a natural laboratory. Unlike experiments on Earth, where we're limited by energy, space, and technology, the universe provides us with collisions involving objects billions of times heavier than our Sun, moving at nearly the speed of light. By analyzing the gravitational wave signals from these events, scientists can test theories of physics under conditions far beyond what we could ever recreate here on Earth. General relativity, nuclear physics, particle interactions, even exotic theories of matter, all can be tested by listening to these cosmic ripples. For example, do black holes always merge exactly as Einstein predicted, or do they leave behind strange remnants? Do neutron stars collapse into black holes after merging, or can they form exotic states of matter unknown to science? Could gravitational waves one day reveal new particles or forces hidden within the universe's most extreme environments? Each detection is like receiving a coded message from the cosmos. Deciphering that code could unlock answers to questions we've been asking for centuries. Gravitational wave astronomy isn't just a scientific curiosity. It's transforming our understanding of where we came from and what the universe is made of. By studying extreme events through gravitational waves, we're uncovering how stars live and die, how elements necessary for life are created, how galaxies evolve through collisions and mergers, and even how the fundamental laws of physics hold up under unimaginable conditions. It's not just about black holes and neutron stars. It's about rewriting humanity's place in the cosmos. And so, the more we tune into this gravitational symphony, the clearer the universe's story becomes. What once seemed silent, distant, and unreachable is now unfolding before us, wave by wave. But this is only the beginning. In the next stage, we'll dive deeper into the cosmic frontiers that gravitational wave discoveries are pushing us toward, including how they connect with the earliest moments of the universe itself. Imagine for a moment that the ripples of space-time we call gravitational waves are not just signals of past cosmic collisions, but stepping stones toward humanity's future among the stars. These faint tremors, born from violent mergers of black holes and neutron stars, are now becoming blueprints for technologies that might one day change how we travel, how we communicate, and even how we imagine ourselves in the universe. We're all familiar with GPS, an invisible lattice of satellites guiding our daily lives. But imagine extending that idea on a galactic scale. Scientists are now asking, could gravitational waves become the backbone of interstellar navigation? Unlike radio signals, which weaken across cosmic distances, gravitational waves pass through matter almost unhindered. They are like whispers that echo undisturbed across billions of light years. If spacecraft could one day detect and lock onto certain gravitational wave landmarks, say, from regularly pulsing binary star systems, they might navigate deep space without relying on Earth-based signals. In fact, researchers at ESA and NASA have quietly been modeling such possibilities. Their early simulations suggest that, much like sailors once steered by the stars, tomorrow's explorers could navigate by the ripples of the universe itself. But here's a problem. The signals are faint, hidden beneath oceans of cosmic noise. To truly harness them, we need more than human eyes scanning computer screens. Enter artificial intelligence. AI algorithms trained on massive datasets from LIGO, Virgo, and KGRA are already outperforming traditional methods in spotting subtle gravitational wave patterns. What once took weeks of cross-checking can now be processed in hours or even seconds. Imagine a spacecraft with an onboard AI that listens constantly to the hum of space-time, automatically identifying nearby gravitational wave sources and adjusting its path. In many ways, gravitational wave detection is becoming less about raw sensitivity and more about intelligent interpretation. This is where AI and astrophysics are fusing into a single field, one that will not only transform cosmology, but also the very engineering of future exploration. Here's a radical thought that sounds like science fiction, but is grounded in serious speculation, using gravitational waves as a form of communication. Radio signals, as powerful as they are, suffer limitations. They can be blocked, scattered, or delayed by interstellar gas and dust. But gravitational waves, they ignore such obstacles. A civilization, human or otherwise, could, in theory, modulate these waves to transmit information across immense distances with zero interference. Researchers at Princeton and Caltech have begun theorizing how such a system could work. The energy requirements today are far beyond us, but history shows that what seems impossible often becomes reality in centuries. After all, radio communication itself would have seemed absurd to Newton or even Einstein. Perhaps the ultimate cosmic internet will be written not in electromagnetic waves, but in ripples of space-time. One of the least discussed, yet most transformative impacts of gravitational wave science lies in resource discovery. How do we know what kinds of stars collapse into neutron stars? How do we measure the abundance of heavy elements like gold and platinum in the universe? The answer: gravitational wave signals. When neutron stars merge, they literally forge precious elements in colossal kilonova explosions. By listening carefully, Astrophysicists can estimate how much material is being created and where. This could guide humanity's search for future cosmic resources. Imagine mining asteroids with confidence, because we know, from gravitational wave records, exactly which stellar systems are enriched with rare metals. Let's take a step further into speculation grounded in physics. Could gravitational waves themselves one day become part of spacecraft propulsion? While we cannot yet generate or harness such waves for thrust, theoretical physicists are exploring how manipulating space-time distortions might become a new frontier of engineering. Some propose that advanced civilizations, if they exist, could already use gravitational control to move massive ships. And here's the wildest part. Even if we can't generate gravitational waves directly, detecting them precisely may teach us new ways of manipulating space-time itself. The leap from listening to waves to surfing them might sound impossible, but so did powered flight just 150 years ago. Another extraordinary aspect of gravitational waves is their role as time capsules. Unlike light, which can be absorbed or scattered, gravitational waves carry unaltered information from the earliest moments of the universe. Astrophysicists are now aiming to detect primordial gravitational wave signals from just fractions of a second after the Big Bang. If successful, these would be the most ancient messages humanity has ever read, predating even the oldest starlight. Understanding these signals could answer whether the universe experienced cosmic inflation, an explosive expansion at its birth. It could even tell us if multiple universes exist. Imagine holding proof of the multiverse, not as speculation, but as recorded ripples etched into space-time itself. As we collect these signals, one fact becomes clear. Gravitational waves are reshaping our identity. We are no longer passive observers of the universe, limited to telescopes and light. We are becoming active listeners of its heartbeat. Every new detection reminds us that we live in a universe both violent and harmonious, chaotic yet patterned. Black holes collide, neutron stars shatter, entire galaxies resonate with hidden music, and now, for the first time in history, humanity is listening. This listening changes how we see ourselves. We're not just residents of one planet or even one star system. We are participants in a grand cosmic symphony, slowly learning to interpret the notes. And so, the discoveries we've made so far are not an end, but a beginning. They push us toward deeper questions. Can gravitational waves reveal dark matter? Can they map black holes that will never shine in visible light? Could they eventually guide us to new, habitable worlds? The universe has given us whispers across space-time, and it is our task to decode them. With each wave detected, we stand closer to transforming what once was myth into measurable truth. So, as we unravel these cosmic ripples, remember every discovery is a reminder of how far curiosity can carry us. Across the vast, silent expanse of the universe, a story is unfolding, a story written not in light, not in sound, but in the trembling fabric of space-time itself. Gravity waves are no longer abstract equations in a dusty notebook. They are alive, real, and echoing across the cosmos. We have listened to the whispers of colliding black holes, felt the faint tremors of neutron star mergers, and glimpsed the hidden symphony of the universe. But the question now stands: what do these discoveries ultimately mean for us, for science, and for the future of human understanding? For centuries, humanity has been trying to decode the language of the universe. First, we learned to see light through telescopes. Then we expanded into radio waves, X-rays, gamma rays. Each new window revealed a universe more complex and beautiful than we imagined. But gravity waves? They are different. They are not just another type of light. They are the actual movement of space-time itself. By detecting them, we are not just looking at the universe. We are feeling it breathe, stretch, and ripple. It's like moving from being an observer to being a participant in the cosmos's unfolding drama. Gravity waves allow us to study phenomena completely invisible to traditional astronomy, black hole collisions, cosmic strings, the birth of neutron stars, and even traces of the Big Bang itself. The detection of gravity waves in 2015 wasn't just about proving Einstein right. It was about unlocking a new method of exploration. Each subsequent detection added to the story the first collision of two neutron stars, which gave us not only gravity waves, but also visible light, an unprecedented double discovery. The identification of intermediate mass black holes, answering a mystery about their existence. Observations that hinted at exotic physics, perhaps even new states of matter inside neutron stars. These were not random milestones. Together, they form a new branch of astronomy that is rewriting cosmic history. We are only scratching the surface. Current detectors like LIGO, Virgo, and Kagra have shown us the first hints. But the next generation of detectors like LISA, Laser Interferometer Space Antenna, in space, and Einstein Telescope on Earth promise something far more revolutionary. With LISA floating in space, separated by millions of kilometers, humanity will detect waves from supermassive black hole collisions at the centers of galaxies. These are events so powerful that their gravity waves could ripple across billions of light years and still be measurable here. We may even detect signs of cosmic phenomena that happened in the first trillionth of a second after the Big Bang imprints of inflation, or exotic topological defects in space-time like cosmic strings. If confirmed, these would change our understanding of not only astrophysics, but the origins of the universe itself. Behind the detectors and data are thousands of scientists, engineers, and dreamers who dedicated decades of their lives to making the impossible possible. The fact that we can now detect distortions in space-time 1,000 times smaller than a proton's width is almost beyond imagination. And this raises an important reflection. What does this say about humanity? That on a small planet orbiting an ordinary star, fragile beings made of stardust built instruments capable of listening to the heartbeat of the cosmos. Gravity wave astronomy is not only about science, it's about human curiosity, resilience, and the drive to know where we come from and where we're headed. Let's pause for a moment and reflect. Gravity waves are telling us that the universe is not static, silent, or cold. It is alive with motion, vibration, and transformation. Think of it this way. Every black hole collision, every stellar collapse, every cosmic event leaves an imprint on space-time like ripples on an infinite ocean. When we detect them, we're essentially reading the autobiography of the universe. This raises profound philosophical questions. If space-time itself can ripple, does that mean reality is more fluid and dynamic than we ever imagined? If gravity waves can carry information across billions of years, does this mean the universe itself is a kind of cosmic archive? And most importantly, are we nearing the limits of human knowledge? Or have we only just taken the first step into an infinite expanse of discovery? Scientists often compare gravity waves to sound. If electromagnetic astronomy radio, visible light, X-rays, is like looking at the universe, then gravitational astronomy is like hearing it for the first time. The universe doesn't just shine, it sings. Black holes merging create bass-like chirps. Neutron star collisions release complex notes that shift in frequency and intensity. And perhaps one day, we may listen to the faint hum of the universe itself, left over from the Big Bang, a chorus billions of years old. This idea that the cosmos is a symphony in space-time is one of the most awe-inspiring revelations in modern science. It's easy to think of gravity waves as only relevant to astrophysics. But history shows that fundamental discoveries often lead to unexpected revolutions. When electricity was first studied, no one imagined smartphones or satellites. When quantum mechanics was developed, no one thought of MRI scans or GPS. So what might gravity wave research lead to? Some speculate about new methods of communication, navigation, or even energy extraction from cosmic phenomena. While these may sound like science fiction, today's science fiction often becomes tomorrow's reality. Each detection of gravity waves tells us one simple truth. The universe is far stranger and far more wondrous than we imagined. Just as Galileo's telescope shattered medieval views of the cosmos, gravity wave detectors are shattering our assumptions about the invisible universe. What lies ahead could be beyond imagination, whether it's uncovering the nature of dark matter and dark energy, probing the earliest moments of existence, or even learning whether our universe is just one of many. So as we close this chapter of discovery, one truth remains. Gravity waves are more than ripples in space-time. They are reminders that the universe is alive with motion, mystery, and music. Each wave that reaches Earth carries with it a story of stars that lived and died, of black holes that collided, of cosmic events that shaped reality itself. And as humanity continues to listen, we may find not only the secrets of the cosmos, but perhaps, in some subtle way, the meaning of our place within it. This is not the end of discovery. It is the beginning of a new way of knowing. The cosmos has begun to speak, and for the first time in history, we are listening. You've been watching Starsky Science, where curiosity fuels discovery. If you found this exploration as fascinating as we have, don't forget to subscribe so you can join us in unraveling the next great mystery of the universe. The cosmos is speaking, and together we'll keep listening.